So ultimately, our objective is to find the area of a region in a plane. And if we look at these couple pictures and we say, I want to find the area under this curve from A to B, from this spot on the function to this spot on the function, and it's going to look like this. Well, what's the shape of that region? I don't have a name for it, but we do know the area of regular figures like rectangles, and we can use areas of shapes that we know to find areas of shapes that we don't know. Area of a rectangle, real easy, just the width times the length. The area is the width times the length times the width. So let's take this region that we don't know and let's break it up into rectangles. If we wanted, now don't sketch this yet because this isn't going to be the best scenario, we could estimate and say, well, let's make one big rectangle, and this is about the shape because I'm including more than I should be and I'm excluding less than I should be, so it's about a good estimate for the area. So let's take the length and the width and let's multiply them and call it a day. However, it's not the best estimate, so we're not going to do that. What we could do is break it up, and again, don't draw this because this is not the best estimate either. Let's break it up into two rectangles. Here's one where I'm only overestimating and underestimating a little bit, and here's another one. Let's find those two areas, add them up, call it a day. But again, it's not as good as it could be. What's even better? Breaking it up into more and more rectangles. Well, let's not get too crazy here and break it up into too much to begin with. Let's, for the purpose of just seeing where we're going to go with this, let's just use 6 rectangles. And when we say we're using 6 rectangles, we also say it like this. We're breaking up the interval on A to B into sub-intervals. So we're breaking it up into 6 subintervals, and we're making those subintervals into rectangles. So 6 means I can split it right down the middle, and you can draw this because we're going to stick with this. And then I'm going to break this first half up into thirds, so here and here approximately, and this one into thirds, so here and here approximately. Now, if I actually had numbers, I would accurately divide by 6, but here I don't, so I'm just going to eyeball it. Go up to the curve, go up to the curve, go up to the curve, go up to the curve. Okay, so I have about 6 subintervals here. When I'm going to make the rectangles using left endpoints, that means here's the first subinterval. Go to the left side of it where the beginning is. Go up to the curve on the left, find a point, go across, and come down. This right here, that's going to be my first rectangle. Again, using left endpoints, here's my second subinterval here. That means go up on the left side of it. Here's the left. Go up to the curve, put a point across, and go down. This is my second rectangle. Third subinterval, go to the left side of it, go up to the curve, across, and down. There's my third rectangle, and so on and so forth. Fourth subinterval, go to the left side, find the left endpoint. Fourth rectangle, fifth subinterval on the left side, up to the curve, over, and sixth rectangle, go to the left side, up to the curve, and over, and down. So I've got my 6 rectangles using my left endpoints. Well, if we're breaking it up, notice how we don't have too much of an over or under estimate here. So that's going to be a lot more accurate than just using one rectangle, 2 rectangles, 3 rectangles. But obviously breaking it up into more rectangles is going to be even more accurate. Let's look at it from right endpoints. So I'm going to try to create the same picture here because it's the same function, and put A and B and show the initial area that we're trying to estimate beneath the curve above the x-axis on this interval. And again, I'm going to divide this up in half and then each half into thirds to make 6 subintervals. But this time, we're going to be using right endpoints. So looking on the first subinterval, but to the right, going up to the function, and now that's the height of my first rectangle, overestimating a little bit. Next subinterval on the right, there's the height of my second rectangle. Third subinterval on the right, there's the height. Fourth subinterval on the right, there's the height. And last subinterval on the right, there's the height. Oh, not the last. This is the last one. Up on the right, and there's the height. So they look different, but we still have some overestimating, some underestimating, and overall the 6 rectangles is better than 1 rectangle. Now, just for the purpose of talking about how we're going to find the area, let's actually go through what we would do to find the area. So the first thing we want to notice is that if we're finding the length times the width of all of these rectangles is the same because we tried to divide it up into equal subintervals. So when we talk about what is the width, we're saying how much x is changing, or delta x, which is, like I said, if I actually had numbers, I would know how long this is, and I would divide it up into how many intervals, subintervals we have. So to know exactly how long this is, we're subtracting the endpoints, b minus a, and dividing by how many subintervals or how many rectangles we have. So n is our number of rectangles or subintervals. In this case, the subintervals we're creating rectangles. My first area, or the area of the first rectangle, we'll list over here on the side, is going to be the width of the rectangle, or the delta x, times the height. Well, the height is the function value we got by plugging in this x coordinate. Let's call it x sub 1. So the function value is the height at that x value. The second rectangle, well, it's the same width. It's still delta x, but now we're plugging in the next x coordinate that we come to. Let's just call it x sub 2. We're plugging it into the function to see how tall it is. So that's delta x times f of x sub 2. Continue in this pattern. Plug in x sub 3, x sub 4, x sub 5, and x sub 6, which happens to be where b is, and those continue to give us our y values. So we do that all the way until the 6th subinterval, and we have our 6 rectangles areas. We want, however, all of those, so these are the right endpoints that we plugged in, we want all of those together. So ultimately we're going to say the area that we want to find is each of the little areas added together. And what's the fastest way to do that? Well, all of them have delta x, so why have to multiply by delta x each individual time? Let's factor out the delta x. Then all we have to do is add up the y values, the heights, f of x sub 1, f of x sub 2, etc., all the way up to f of x sub 6. We multiply our common width that we factored out times the sum of the heights, and we have our area. So that's where those are going. Now, because this is an estimating technique, let's talk about how we're estimating and what kind of results we get when we estimate this way. Because we're only breaking it up into a certain number of rectangles, we're overestimating a little bit here, underestimating a little bit here. So there's some over and underestimating, and we want to know, when does that happen? So let's look at the picture when we do left endpoints. So with the left endpoints, when is it that the rectangles are going to overestimate? Here's an underestimate. Here's an overestimate. Here's an overestimate still. Now it's an underestimate, slightly under, but still under, under, under. When is it overestimating? This section right here where the function is below the height that we got from taking the left endpoint. So when the function is decreasing, it's an overestimate. Overestimate when our function, and we're going to call this f of x because that's what we've been doing so far, when f of x is decreasing. Similarly, it's the underestimate when f of x is increasing. Is that the same when it's right endpoints? Let's look at the picture. In the picture here where there's right endpoints, where is the function, where are the rectangles, the rectangles overestimating? Overestimating here because the right side is taller on this increase. Overestimating here, overestimating. Every time the right side is higher, the right side will be higher when the function is increasing. So we get an overestimate for the right endpoints when f is increasing. And similarly, an underestimate with the right endpoints when the function is decreasing. Know this. Even if you just know how to recreate it, know it. Let's talk about where this is leading us to. We want ultimately not an estimate of the area, but an exact area. Not an estimate, but an exact area of a plane region. Whether it's a regular shape or not, we want an exact area. So what would be better than 6 rectangles? 7, 8, 9, 100, 1,000? Keep going. Let's take the number of rectangles to infinity. Now, can we actually do that? Can we take an infinite amount of rectangles? No. So that's where limits comes in. The exact area that we're going to find, the exact area, will be the limit as we take the number of rectangles to infinity of the sum from the first rectangle we add to the last rectangle, which remember is going to infinity, of the area of each rectangle. Well, how did we find each rectangle? We did the width times the function value. So that's how we're going to write it. The width, delta x, times the function value. But I'm going to write this as f of c sub I. So let's make a note to remind how did we find the width? The difference in the endpoints of the interval, how long is the interval, divided by how many subintervals that we have. So remember, this was the width. Delta x gave us the width of each of our rectangles. And just as another reminder, n is the number of rectangles. We also called it the number of subintervals. F of c, or f of c sub I, is the height. And we can do that height using right endpoints or left endpoints. I'm going to take it with the right endpoints because I think it is a little bit easier to follow. The x value that we get is delta x units away from the starting point. The next x value is 2 of those delta x units away. The third x value is 3 of those delta x units away from the starting point. So that means c sub I is the starting point plus I amount of delta x's away. Let's look at that again so that you're sure. Here is the starting point A. The first x, the second x, the third x, so on and so forth until we get to the end of the interval. Each of these subintervals is delta x big, delta x big, delta x big. That's the width. So to get x sub 1, to get that x coordinate, that is the c sub I. So the first c sub I is c sub 1, this one. Start at A and add 1 delta x. Then c sub 2, this x coordinate, is start at A and add 2 of those delta x's. Continue in this pattern, start at A and add 1, 2, 3 delta x's. And what we're doing is that value is how many delta x's we are away from A. C sub 2 is 2 delta x's away. C sub 3, 3 delta x's away. So C sub I is I delta x is away from the starting point. So remember what this is. This is the area of each rectangle. This means we're going from the first rectangle to the nth rectangle, and we're breaking it up into infinite amount of rectangles. And that's how we get our exact area. Go to the next video to see